All right, so to wrap up this kind of cute little one-off section, I want to jump back to our initial question of trying to decompose some primes as a sum of squares, but then expand it not to just primes. Basically, can I do better than just primes? So can I take some number like 65 and can I decompose that thing as a sum of two squares? And the answer is absolutely, because 65 is one more than a perfect square. So it will definitely work because it's 1 plus 64, which is then 1 squared plus an 8 squared. So I know that some other numbers can also be decomposed as a sum of squares, but I want to essentially lean on the prime structure that we have before to start to see where this is all actually going to go. And I'm not going to go full into the weeds on this. It's basically just one of these little reminders that these primes become the building blocks to the other numbers. So if you have results for the primes, it'll then sometimes carry up to more general numbers as well. So the number 65 can be decomposed, i.e. factored into a product of primes, namely the numbers 5 and 13. 5 and 13 actually both have a sum of squares representation. So 5 is 1 and 4, and 13 is 4 and 9. So down below is going to be this cheesy little way that I can take a product of a sum of squares and actually convert it into just a nice little sum of squares on its own. So I tried to keep these things nice and color coordinated. So I have the 1 and the 2 coming from the 5 and the 2 and the 3 coming from the 13. So if I were to basically take the 1 and the 2 and the 1 and the 2 in the same slot, and then the 2 and the 3 from the other one, and then spin them around and have the 3 and the 2 with a negative, if you were to expand out what those things actually become, the left-hand side becomes 2 and 6, which is an 8. The right-hand side becomes 3 and negative 4, which is a negative 1. And if you square those things, it becomes 64 and 1, which adds up to 65. So that's a little bit of kind of what's behind the scenes. If you want to jump it into some nice variables, which I recommend because it showcases a little bit more of what's happening. If you give me any n that is decomposed as p times q, well, if the p and q have a decomposition as a sum of two squares, then so will n. N will in fact have this representation right here. So the way that you can see that is you have my p, which is a squared plus b squared, and my other one is c squared plus d squared. So the decomposition into a sum of squares is going to be the a and the b's are going to be in the same spot on both of those things. And then I get, on the other side, I get the c and the d, or the d and the c on the back end, and that one's going to come with a negative sign. The right-hand one maybe looks like a determinant if you've ever done a little bit of linear algebra, which again, there's tons and tons of connections into these lattices and things like that. So it's again, just this tiny little kind of poking into the iceberg of this thing, but there's a snowball approach that you can do after this as well. So we have n, which is a product of p times q, which I'm claiming then can be represented as a sum of squares. If you want to show this, so if you want to show why this equality actually works, I would recommend starting with the right-hand side, blowing that thing up and actually seeing what's going to happen. So that's not the way that we use it, but it's the way that we then verify it. So if you take AC plus BD and AD minus BC, and if you square those things, so if you represent them as two little binomials and do the foiling side of things, you're going to get, for the first one, essentially AC quantity squared, which is A squared C squared, and you're going to get a b squared and a d squared. And then your mixed term in the middle is going to be a, b, c, d, and you get two of them. So you get two a, b, c, d. The exact same type of thing is going to happen on the back side, except for you're going to get a mixed term that has a negative. And that's coming from that negative, which means those two things kill each other off. So you're left just with the little squared terms. So a squared c squared, b squared d squared, a squared d squared, and b squared c squared. So then to clean everything up, you actually look at this term, which has an a squared in it, and you look at this term, which has an a squared in it, and you factor out the a squared, leaving you with c squared plus d squared. For the other one, you're going to see that this thing has a b squared, this thing has a b squared, so you factor out the b squared, leaving you with c squared plus d squared. And then that expression at the end has shared c squared plus d squared, so you can factor that thing out, leaving you with a squared plus b squared multiplied by c squared plus d squared. So you get this evaluation to actually work out. So I skipped some of the details, but I would highly recommend trying to sketch those out just because it's kind of cute to see all of that stuff emerge. And it does give us this really easy way then to take any n that's represented as a product of p and q and decompose it as a sum of two squares. So if I have n, which is 1313 multiplied by 8675309, both of those primes have a decomposition as a sum of squares. So I can then feed that into my little formula from before. So this would be my A, that would be my B, that would be my C, that would be my D. So A and B and A and B, and you have C and D and C with the negative. And if you clean those things up, you're going to get whatever 42,959 quantity squared, as well as 29,494 squared. If you were to add a third, let's say Q into the mix, well, then you would have this part can now be represented as some a squared plus b squared, and your q would be some c squared plus d squared, and you could rerun that process again. So there's this nice recursive version that if you have your n, which is represented as a product of any number of primes p and q that are all having this being a 1 modulo 4, then you always know that you can recursively call this thing and start to see these sum of squares emerge over and over and over again. That one takes a little bit more effort if you were to try to go up that rabbit hole or down that rabbit hole, depending on how far you want to go up or down. You can start to see some of those things. But I do have a couple of the examples just on your exam/activity for that, where you'll have your earlier decompositions from some of the earlier problems, and then some of these cute little one-offs of like, well, can you also do this thing with it? If so, neat. If not, try something else. It does cycle back into some of the earlier factorization algorithms that we saw back when we were doing RSA stuff, in that we have this sum of squares actually led into some factorization techniques. So this is basically kind of doing the other side, is that if you have this p times q, you can decompose it into a sum of squares. Well, if you have the sum of squares, it'll actually lead into the factorization as well. So they all start to mix on each other a little bit, but I figured it was worth at least poking into a bit just because it made some cute little questions that I wanted you to poke around in. So enjoy. So as always, if you got any questions, let me know. Otherwise, have fun.